filling up the car with petrol at a service station. So what's the link between this and these? The answer is they all use products that come from oil. Cars use petrol, trains and buses use diesel, planes are fueled by kerosene, and roads are covered by tarmac. Plastic bags can be made using a substance called naphtha, and gas that is found with oil can be used to generate electricity. Yet all these different substances come from just one raw material called crude oil. How?
In the flask, you've got ethanol, which is an alcohol, and you've got water with a bit of dye in it. This is just to show the process of distillation, okay? All right, you can see now at the moment, you can see the ethanol and the water starting to heat up a bit.
This classroom experiment is separating two substances, water mixed with ethanol. The water with red dye has a boiling point of 100 degrees Celsius, but ethanol boils first at a lower temperature, rising up the column as a gas. It leaves the red water where it started, and over here will drip pure clear ethanol once it's cooled and condensed back into a liquid.
You can actually see something dripping, it's coming through, and you can see it's clear, it's not red in any way whatsoever. It's clear, yeah. So this is a really small scale version of what they might do in industry.
On a much grander scale, inside these huge pieces of equipment at an oil refinery, the same basic activity is going on. Crude oil is being heated up and separated into different substances. Fractions they're called here. So what are they?
It's the refinery distillation countdown. Let's start with the breakers.
In at the bottom and very hot is bitumen, used to waterproof roofs and tar roads.
Bubbling under.
Fuel oil, used in ships and power stations.
Rising to 330 degrees.
Lubricating oil, used to reduce engine wear.
Up at 250 degrees.
Diesel oil, used in buses, lorries and trains.
High climber at 150 degrees.
Kerosene, used as aircraft fuel.
Moving at 70 degrees.
Naphtha, it's used to make plastics, medicines, fabrics, fertilisers and perfume.
At 40 degrees.
Petrol.
And at the very top.
Petroleum gases, used as camping gas, gas fires and in the manufacture of plastics. It's not a new process.
The first record we have of petroleum used by man was the sticky pitch seeping from the ground in the Euphrates Valley. The pitch oozes from the rocks and finds its way to the nearest stream. Through the centuries, this soft pitch has been collected for lighting dwellings, for fires, and as healing ointment for men and animals.
Men and animals? What happened to the women? Anyway, as ancient man had no use for petrol, diesel or fuel for aircraft, they burnt it, leaving that thick gooey tar that they called pitch. And it wasn't the most scientific of processes.
The quality of the pitch is judged by rolling it between finger and thumb, a good example of the rule of thumb.
It's now a precise and skilled science in oil refineries, so let us be a little bit more scientific and precise. Heated crude oil is fed into the bottom of the refinery distillation column, and boiling off at the top are what's called petroleum gases, with names like butane and propane.
Hydrocarbon molecules consist of hydrogen and carbon atoms. Carbon atoms form strong bonds to make chains. Fractions with short chains boil at lower temperatures and burn well. Petroleum gas molecules are in short chains.
These gases burn very well, and a common use of one of them, propane, is to be sold in these heavy metal bottles as camping gas and for gas fires. Petroleum gases are also very important in the chemical industry for making plastics. Before we reach the next fraction to boil off, a commercial break from your grandparents' days.
Well, wake up at the back there, will you?
Morning, Mr. Edwards.
Ah, there you are. Fill her up, will you? I'm almost out of gas.
Right, sir.
Not me, Kitty Winkies, the car. Jim's always gassing, as you know.
I'll give you 6 of the best, sir.
Hey? Oh, you had me worried for a moment.
By the best, sir, I mean BP Super. That's the petrol you need to keep the engine clean.
Well spoken, lad.
And that means longer life for your engine.
And jolly good health to you, too. Little does he know that I am a BP Superman.
Gas, he called it. And the Americans still do. We know it as petrol. Proper name, gasoline. You'll see its molecules form a slightly longer chain than the petroleum gases. It doesn't burn quite as well either. In fact, the chains will continue to get longer as we move down the distillation column. Naphtha is next. It has a longer chain, and though it's least well known, it produces the most familiar everyday objects, like this polythene, that will make cling film and bags. Along with natural and petroleum gases, it's the basis for the petrochemical industry, where we get plastics, medicines, perfumes, even de-icers.
BP has developed a new runway de-icer, which is more effective at clearing snow and ice. It's also kinder to the surrounding countryside, which is reassuring, however you choose to fly.
The next fraction to boil off is kerosene. It's mostly used as fuel for aeroplanes, Jet A1 they call it. Without it, there'd be none of this. No beach holidays abroad, or not by plane anyway. And on the science side of things, the chain molecule is getting longer as the boiling temperature increases. Next to boil off are gas oil or diesel fractions. As I've already said, diesel is used to fuel taxis, lorries, buses, trains and the like. It's also used for central heating. And that leaves what the refiners call residue, the leftovers. Though nothing is wasted, not least because there's so much of it. Before it is used for anything, it needs further processing. Then it will become wax for crayons and candles, bitumen for road surfaces and lubricating oils. And here's how they once advertised lubricating oil.
On March 23, 1968, 2 production cars set out on one of the most harrowing tests ever run in southern Africa. The purpose? To prove the phenomenal protective powers of a new generation motor oil. No torture was spared, no road condition overlooked. In country and in city, years of ruthless punishment were compressed into a few short months. If there's a motor car's hell, these 2 cars know what it's like. But by May 27, the agony was over. Under the watchful eye of the AA, the cars were stripped, their parts examined by the most sensitive measuring instruments. Yet no meaningful wear could be detected. The new generation motor oil.
But separating oil fractions into products is just the first stage of the process. For some, the next is conversion. Have you ever had a pack of sweets like this? Some of which are favourites and others you hate. But you get as many of the ones you don't like as the ones you do.
Just watching, I'm not trying to do Can I do it?
The same goes for oil. Refine oil because you need petrol, and you still get kerosene, butane, bitumen and the rest, whether you want them or not. Fortunately, massive refinery equipment like this can turn the unwanted products into ones that are wanted, splitting the large hydrocarbons into smaller ones. It's a process called cracking. Heat breaks the bond between the carbon atoms, a process helped by catalysts.
Catalyst, a substance that changes the rate of a chemical reaction, but which remains chemically unchanged itself.
A long-chain hydrocarbon that's not much use as it is will, when passed over a catalyst, split apart into something more useful. The result is something with a shorter molecule and something else called an alkene.
So when kerosene is passed over the catalyst aluminium oxide, you get octane, which is useful for petrol, and ethene, used in making plastics.
Right, next, cleaning the products. Let's look at what happens when you burn hydrocarbons. In this test, a wax candle. When there is complete combustion of hydrocarbons, they burn cleanly and are non-poisonous. Carbon dioxide and water is formed. And the water makes the cobalt chloride paper go blue.
It's gone
Yeah.
When there isn't enough oxygen, combustion will be incomplete. So as well as carbon dioxide and water, that black smoke is unburned carbon. There can also be carbon monoxide, that is colourless, odourless and poisonous. But you may also know about acid rain. It pollutes water and kills trees. It's caused by sulphur dioxide released to the atmosphere, mixing with clouds and turning the rain into a dilute sulphuric acid. And what causes it? Burning hydrocarbons that contain impurities like sulphur. So in the refinery's cleaning stage, it removes sulphur along with other pollutants. All this takes up space. This refinery in Grangemouth, central Scotland, extends over a mile. Dominating the skyline are those huge towers. So what's that coming out of them? A, sulphur. B, gas. C, water vapour. D, carbon dioxide. The answer is C, water vapour. Many of the chemical reactions in the refinery are exothermic.
Exothermic, a reaction that gives out heat.
That means a lot of water is needed for cooling. Inside this tower, water that has been used for cooling and has become hot in the process is sprayed from the top and cools again as it falls. So by the time it reaches the bottom, it's ready to be used again to cool more processes and chemical reactions in the refinery. The Grangemouth complex has 4,828 kilometres of pipe, and every day around 200,000 barrels of crude oil flow through them to be refined into the products we've seen. And since this programme started, the refinery has made enough petrol to drive a car almost 1 million miles. That's 40 times around the world. And it keeps on working, refining oil for products every day, every night, every year.